Hello, welcome to Equity Education, the chemistry version. And today we're going to be looking at lattice enthalpy. Okay, so I'd like you to open your booklets and we'll get started. Okay, so lattice enthalpy. We're going to have quite a lot of definitions that you have to learn today. Yeah. Okay, so you must learn these and you must understand them as well because they will help you to construct these Born Haber cycles, which we'll talk about later. Okay, so our first definition is of lattice enthalpy, and we can describe lattice enthalpy as, well, first of all, we'll do our symbol. So this is our symbol, delta H, under standard conditions with lat at the bottom. So it's the energy released when 1 mole of an ionic compound is formed from its constituent ions in their gaseous states under standard conditions of, our standard conditions are 298 Kelvin and 100 kPa, kilopascals. Okay, first definition. And we can say that lattice enthalpy is always exothermic. So it is always exothermic. And an example might be if we had, let's have Na plus Cl minus. So these are my constituent ions. They need to be in gaseous states. So G, and forms our NaCl. So this is an example of a lattice enthalpy equation. Okay, so we'll move on. So the more exothermic the lattice enthalpy, the stronger the ionic bonds between the oppositely charged ions, which makes sense. And lattice enthalpy is theoretical. Gases don't really combine. We work out lattice enthalpies using a Born Haber cycle. Okay, so Born Haber cycle, and we'll have a look at one. And then you're going to start to construct one. So this is my Born Haber cycle for lithium fluoride. And I'm just going to label some things here, so I need you to do the same. So we'll label this as delta HF as G, and then A, B, C, D, and E. Okay, and a bit like a Hess's law cycle, we know that if you look here, just here, we know that root 1 is equal to, all the way around, root 2, which means that my G is equal to A plus B plus C plus D plus E. Makes sense so far, I hope? Yeah. So my root 1 equals my root 2, and which is the same as saying G equals A plus B plus C plus D plus E. So the idea of these Born Haber cycles is to find out an unknown. It's either the delta H formation or the delta H lattice, usually. Okay, but before we get on to the calculations, we are now going to do some more definitions. Okay, so our step 1. So step 1, this is our step 1 here. And our step 1 is the enthalpy change of atomization of lithium. And this is the enthalpy change when 1 mole of gaseous atoms is formed from the element in its standard state. And our symbol for atomization is delta H AT. E.g., so in our example up here, lithium has gone from a solid, because that's its standard state, into a gas in 1 mole. So we can show that as lithium S goes to lithium G delta H at of lithium. Simple so far. Okay, step 2. So my step 2 here, thing which is changing is my F, my fluorine F2 is, my step 2 here, lithium, is losing an electron. Yeah. So we call that, which you may have seen before, step 2 is the first ionization energy. But it's usually called first ionization energy. You may see it called first ionization enthalpy. That's why I've included it. Of lithium. So the first ionization enthalpy or energy of lithium, symbol is first IE, and this is the energy required to remove 1 electron from an atom in 1 mole of gaseous atoms to produce 1 mole of gaseous positive 1 ions. Bit of a mouthful, yeah? So we'll read it again. The energy required to remove 1 electron from an atom in 1 mole of gaseous atoms to produce 1 mole of gaseous positive ions. You may see it worded slightly differently in different textbooks. That's fine, and we'll stick with this definition. And if we're going to write it, we'll use the example up here. So we'll be using lithium. So the energy required to remove 1 electron, 1 electron from 1 mole. Let's just draw it and then I'll read it. That's E minus. So the energy required to remove 1 electron from an atom in 1 mole of gaseous atoms to produce 1 mole of gaseous positive ions. So 1 mole, and this would be 1 mole. I need to include my state symbols, so gas and gas, and this would be my first ionization energy. Okay, right, so moving on. Now, just as a quick point, this isn't in our Born Haber circular example above. However, you may get second ionization's energy as well, so we better just define it. So, second ionization energy is the energy required to remove 1 electron from each positive 1 gaseous ion in 1 mole of positive gaseous ions to form 1 mole of positive 2 gaseous ions. So I read it again. The energy required to remove 1 electron from each positive 1 gaseous ion in 1 mole of positive 1 gaseous ions to form 1 mole of positive gaseous 2 ions, e.g. Let's use X as example. So this time I'm starting off with a positive ion, and I'm losing another electron to produce positive 2+. Yeah, and we can do the third ionization energy, and the fourth ionization energy, and the fifth, and so on and so on. And you can use exactly the same format. Okay, so step 3. So step 3, let's have a look at step 3 here. So this is my step 3 here. And what's happening here? What's happening? So something's happening with the fluorine here. So it's gone from half F2 to F. So this is the enthalpy change of atomization of fluorine. And I haven't defined this because we've already defined it up here, that's why. So enthalpy of atomization is the enthalpy change when 1 mole of gaseous atoms is formed from the element in its standard state. So here we would have half F2 gas forms F gas. Remember, in our definition, it's to form 1 mole of gaseous atoms here. Yep, so we need half over here. Step 4, okay, so this is a bit different, is what's happening. So F is gaining an electron to produce F minus. So we call this the enthalpy, the first electron affinity of fluorine. And we can describe this as the enthalpy change when 1 mole of an atom gains 1 mole of electrons. So the enthalpy change when 1 mole of an atom gains 1 mole of electrons. And we'll just write that the first electron affinity is always negative /exothermic. Okay, I don't think I've left enough space note, so just quickly at the bottom we'll write it in. So we've got our F gas plus E minus forms F minus gas. So when 1 mole of an atom, gaseous atom, gains 1 mole of electrons to form 1 mole of F minus gas. Okay, so we'll just fill this out and then you can have a go at answering. So the second electron affinity is always positive. Okay, so I'd like you to just have a think about it and see if you can answer this question. Okay, so I've got a pre-filled answer for you, so I hope you managed to get this. So the second electron affinity is always positive. Why? Adding an electron onto an already negative ion means that there is repulsion, therefore requires energy. Pretty straightforward. Okay, so we'll carry on. So step 5. Step 5 is actually my enthalpy change, my lattice enthalpy, which we've already defined. So I will just write it as the, that's my lattice enthalpy. And the root 1 is our last definition, which is when solid lithium and fluorine gas forms LiF. And this is the enthalpy change formation of lithium fluoride. And we describe this as the the enthalpy change when 1 mole of a compound is formed from its constituent elements in their standard states. So if I was going to write this, we'll use lithium fluoride as the example. Lithium plus fluorine forms lithium fluoride, solid. So lithium in its standard state is solid, and fluorine is a gas, and it forms 1 mole of our compound. Okay, so there are all the definitions that you need for the time being, so we'll go on to calculating lattice enthalpy. So calculate the lattice enthalpy of LIF given the following data. Okay, so if we go back up here, we can see that G, so my enthalpy change of formation, is equal to A plus B plus C plus D plus E. We're trying to calculate E. So we want to calculate E. So I can rearrange this to make sure that E, go all the way back down, E equals G minus A plus B plus C plus D. Now I'm not going to do it all the time, but I am going to write them out very quickly, just so, because you have to do them in the exams. So this means that it would be my delta H lattice is equal to delta H formation of LIF. Let's do property LIF minus A, which was my delta H atomization of Li, plus my delta H, what was my next one? First IE of F plus delta H atomization of F of, sorry, first ionization energy of lithium. Let's get it right. So what happens when I try and do it from memory? Of lithium, atomization of F plus delta H first EA of F, and I think that's it. A plus B plus C plus D. 1, 2, 3, 4. Yes, it's right. So now we can just stick in our values. So this would be minus 606 minus brackets 159.4 plus 79 plus 520 plus minus 320, which gives me a value of minus 1044.4 kilojoules per mole minus 1. Okay, so pretty simple. All you need to be able to do is rearrange an algebraic expression, and you should be able to calculate any enthalpy change which is missing in the diagram. Just be careful when you do come to calculate these that you understand the definitions. Okay, it's always for 1 mole of something, because you might have to adjust these values dependent on the definitions. Okay, so now it's your turn. So what I'd like you to do is construct a Born Haber cycle and calculate the enthalpy change of formation of MgO given the following data. Okay, so have a go at this, and I will see you back here in, I don't know, about 10-15 minutes. Okay, so hope you got on all right. I've left a page at the back just in case it didn't go so well, so you can fill it out there or here. I probably should have said that before I started getting you to do this. So I've quickly drawn my Born Haber cycle and we'll fill it out together. Okay, so we'll start down here. So I have my Mg in its standard state and my oxygen in their standard state, and if I go down here I form MgO, which is my solid. So to go from magnesium, 1 mole of magnesium magnesium in its standard state and oxygen in its standard state to form 1 mole of magnesium oxide, going down, this would be my data, my enthalpy of formation of MgO. So this is my root 1. Okay, so now we need to do the root 2 and go the other way. So the first thing I need to do is atomize my magnesium. So the energy required to change 1 mole of magnesium in its standard state to 1 mole of magnesium as a gas. Let's show that as a gas better. Plus half root 2 gas. So this will be my enthalpy of atomization of Mg. My next stage is, now it doesn't really matter which way around you do it, I'm going to atomize my oxygen first, plus delta H, whoops, excuse me. So my O, my oxygen has now been atomized, so this is the enthalpy of atomization of O. Now I need to gain an electron gas. So this would be my first ionization energy of Mg. And you may have noticed I've run out of space. We need a charge of positive 2. This is gas. Don't forget to do the state symbols. This is gas here for my magnesium. Plus O gas. So this is my enthalpy change for the second IE of Mg. Remember, magnesium is in group 2, oxygen is group 6, so we're going to have charges of Mg2 plus and O2 minus. Okay, so we've got our first and second ionization energies of Mg2 plus. This is gas, remember, if you can't really see it, that should be a gas. And now we need to do our electron affinity of oxygen, so adding our electrons to oxygen. So this here would be my first electron affinity of O. So we would have Mg2 plus gas plus O minus plus E minus. So I've added 1 electron onto my O minus, and now I need to add, let's get this in the right place. Arrow should be here. I'm going to have my second EA of O, and this arrow is going back up, and that's because, as you answered the question earlier, I'm adding an electron on something that is already negative, so it's going to require energy. So this is gas, and this is gas. So I now have my ions in their gaseous state, which must mean that going from here to here must be my enthalpy lattice energy to MgO. Okay, I hope you got that, I hope it makes sense. And we will quickly do the calculation. I'm not going to write out all of these again because I've already done one example of it. You should though. However, what are we calculating? I forgot. The enthalpy change of formation. Yeah. So my root 1, this is my root 1. I'm calculating this. So my root 1 equals my root 2 going all the way around. Therefore, I'll just stick in the numbers. I would have 148 plus 249.5 plus 738 plus 14.51 plus 798 plus, I'll put these in brackets, minus 141 plus minus 3791. So these two values are my lattice enthalpy and my first electron affinity because they're negative, and this should give you a value of minus 4547.5 kilojoules minus 1. Okay, hope you got that as the answer. Hope you were able to construct this Born Haber cycle. The things to remember in the Born Haber cycle are you have to write in the notations. So for example here, enthalpy change of formation of MgO. You have to make sure you get the correct standards, the state symbols in as well. Okay, so make sure you have the correct state symbols and make them look like S's and gases, unlike I've done on mine. Right, so let's have a go at answering this question. So why do you think the value of lattice enthalpy is so much more negative for MgO compared to LIF? Okay, so I'll let you have a think about it and you can revert back to your LIF lattice enthalpy and we will discuss it in a second. Okay, hope you got this then. Right, so, well, the simple answer is that we must have stronger forces of attraction between the ions, okay? And we can go on to explain this in a bit more detail on the next page. Okay, so that's our simple explanation. The stronger force of attraction is going to require more energy to overcome. Okay, so trends in lattice enthalpy. So these are the things that affect the value of lattice enthalpy. The first one is size of the ions. So if the ions are small, as in the radius is small, so have a small ionic radius and have the same charge, the ions will form a stronger lattice. E.g. we can use calcium oxide, which is minus 3401 kilojoules per mole minus 1, and BaO, which is minus 3054 kilojoules per mole minus 1. Run out of space. So we can explain this as the larger size of the barium ion means the center of the anion and cation are not as close, therefore there is a weaker force of attraction. Okay, makes sense? Yeah, don't think there's any more explanation needed for that. Okay, and next point is the charge of the ion. So as the charge of the ion increases, lattice enthalpy becomes more exothermic, e.g. not going to be able to fill in the kilojoules per mole minus 1, but you know what it is. So Na2O is minus 2478 and MgO is minus 3791 because the force of attraction between the Mg2 plus, so cation, and the O2 minus, for example the anion, is stronger. So quickly just go over that. That's obvious as well. I think that Na only has a charge of +1, Mg has a charge of 2 plus, therefore the increases charge has made the strength of attraction increase between the MgO compared to the Na2O. And I'm just going to write this down here is, so if we combine size and charge together, we have something called charge density. So you may see this described as just charge density. So if we have a high charge density, it must mean that we have a high charge, and a small ion. Okay, I've separated them here. Okay, and lastly, polarization of ions. So polarization is the distortion of the electron cloud in a molecule or ion by a nearby positive charge. In ionic compounds, metal ions distort the outer electrons of a negative compound, negative ion. This means there is significant covalent character in the compound, leading to a stronger force of attraction, and lattice enthalpy numerically increases. And it gets more exothermic, basically. Okay, I'm just going to draw a diagram, a very quick one. So, positive, negative, positive. Let's change to green. Negative. Okay, so we'll describe this. So if we've got a strong positive cation here, and we have a negative ion here, what actually happens is that the outer electrons are attracted towards the positive cation, and that means that we introduce covalent character into this compound. And as soon as we start introducing covalent character into this compound, we increase the strength of the bond. So that means that there will be a stronger force of attraction. Okay, I hope that makes sense. So, combination of these factors. Right, so it's hard to accurately assess what factors are the most important when discussing lattice enthalpy. It is generally considered that charge on the ion has the greatest effect. So that means that you'll probably be given two compounds and asked to discuss why one of them has a greater or more exothermic lattice enthalpy than the other. So all you have to do is fit these three examples, three factors in with the values you're given. So look at the charge, look at the size, and you can discuss polarization if you think there's any. Okay, right, so what are we up to now? Okay, so we're going to move on to a different type of Born Haber cycle. So another type of Born Haber cycle can be used to explain the energy released of substances in water. So when a substance dissolves in water, it's the energy released, or the energy which is required. I shouldn't really say energy released. Sorry, let's get rid of this word. We'll just put energy, because it could be positive, it could be negative. So another type of Born Haber cycle can be used to explain the energy of substances in water. So when it's dissolved in water. And again, we got some more definitions. So enthalpy change of solution. So the enthalpy change when 1 mole of an ionic solid dissolves in water. E.g., let's use sodium hydroxide as an example. So we have it as a solid, we add water to it, and I will get 2 ions because it's an ionic compound. So my Na plus, Cl minus will be ions that can move around. Oops, not OH, Cl minus. Sodium chloride all the time. OH minus as my example. So my sodium hydroxide has been solved in water to produce Na plus and plus OH minus. And this would be my notation, enthalpy change the solution of NaOH. Okay, the enthalpy change of hydration. So the enthalpy change when 1 mole of a gaseous ion is completely hydrated by water under standard conditions of 298 K 100 kilopascals. So the energy change when 1 mole of a gaseous ion is completely hydrated by water under standard conditions, e.g. we'll use Na+. We'll just write it down, so it needs to be gases. It's completely hydrated, so I'll just put plus AQ. Use the Na plus AQ. And this would be the enthalpy change of hydration of Na. Okay, that makes sense so far? Yep. Okay, so the enthalpy of solution of substance can be calculated by using the enthalpy of hydration value and I'm going to write this, lattice enthalpy dissociation. Okay, so the lattice enthalpy dissociation, which is the energy required to break up 1 mole of an ionic compound. The difference between these two values gives us the enthalpy of solution. Okay, and this is important in some courses. The reverse of the enthalpy lattice is used. Make sure to check which term you should be using. So, what do I mean by this? I will just give you a quick example. So, Na plus gas plus Cl minus gas forms NaCl gas. Don't write this down just for a second because we won't have enough space. It goes to solid. So technically this is my enthalpy lattice. Okay, so the reverse of this, so going from NaCl to Na plus gas plus Cl minus gas, would be called the lattice enthalpy dissociation. However, in some textbooks and in some boards, all they call it again is lattice enthalpy, which is very confusing because you don't know which way around it goes. So I will use the phrase lattice enthalpy dissociation, which would then be the the reverse of. Pen stopped working for some reason. Okay, sorry about that. Slight technical hitch always seems to happen when it's going quite well. Right, so what was I saying? Okay, so my lattice enthalpy dissociation will be the energy required to break 1 mole of an ionic compound to form gaseous ions. So technically it would be this, yeah? Okay, however, sometimes they just call it lattice enthalpy, which gets very confusing, so I've used a different term. Okay, right. After all that, I'm going to rub that out, because I've explained it now, and we're going to do another equation. So, I don't remember what we were talking about. Let's get back. Let's get my head back in the game. Right, so, enthalpy of solution. Right, so, my equation for working out enthalpy solution equals my dissociation lattice enthalpy plus my delta H hydration, or if you're not using the dissociation definition, you can just do minus the lattice enthalpy, just stick a negative there. Okay, so the enthalpy of hydration is energy released due to the attractive force between water molecules and the positive and negative ion of the substance, which kind of makes sense, doesn't it? So since we're doing water, we can use blue. So here are my water molecules, and then I'll have Na plus here and Cl minus down here. So it's an attractive force between the water molecules and the aqueous ion. So there's always going to be a force between these positive and negatives, and it's this energy that's released that we call the enthalpy of hydration. Okay, moving on. So the enthalpy of hydration becomes more exothermic where there is a large charge on the ion and when the ion is small. Therefore, enthalpy of hydration becomes less exothermic down the group. So, although the charge wouldn't change down the group, the ion is going to get bigger, which means it will become less exothermic. We can also say, remember, that if we have a high charge density, that it will be more exothermic, the value for the ion. It's pretty much the same reasons that we were talking about for lattice enthalpy, so I don't really want to go into that much detail on it. Okay, so calculating enthalpy solution using a Born Haber style cycle. Using data below, construct an enthalpy of solution cycle for NaCl, and I'd like you to calculate as well. Okay, so I think you can have a go at doing this yourself. I've left a page at the back so you can have a practice if you want, and then we'll go through it together. Okay, so have a go, and I'll be back in a minute. Okay, so made my cycle, and we'll go ahead and fill it out and see if yours looks like mine. So here I have my sodium chloride as a solid, and we are going to go up. So this would be my enthalpy of dissociation, lattice enthalpy. So we would form our yes molecules at the top, and then I can work out my enthalpy of hydration going down here. So we'll do sodium first. So this would be my enthalpy of hydration of sodium. And going down here, we would have my enthalpy of hydration of Cl minus, and this would form Aq plus Cl minus Aq, which means here is my enthalpy change of solution of NaCl. I haven't put an arrow on this one here yet, and you probably know why if you've done the calculation. So if we do our calculation, enthalpy change of solution is equal to my enthalpy of dissociation of lattice enthalpy plus the enthalpy of hydration of sodium plus the enthalpy of hydration what are we doing? Cl minus Cl. So this gives us a value of plus 780 plus minus 418 plus minus 338, giving me a value of something plus 24 kilojoules. Kilojoules per mole minus 1. So that means my arrow must be pointing up because it's positive. Yeah. Okay. So this is an example of enthalpy, a Born Haber cycle for enthalpy of solution. Okay. You may see that the NaCl enthalpy of solution is on the right hand side. Usually, if it's an endothermic process, you might see on the right hand side, but it doesn't make any difference. Okay, you can just leave it on the left. Okay, doesn't matter. Okay, so, and lastly, we'll just fill this out. So the enthalpy change of solution is endothermic, which you think is quite surprising because NaCl will readily dissolve in water, but it's an endothermic process. So this means that there must be another factor when looking at the solubility of a substance, and we call this factor entropy. And entropy is what we're going to be discussing on our next exciting instalment of chemistry from Equity Education. So, hope you learned something, hope it was useful, and I will see you next time. Okay, bye-bye.